So today I'm going to take you on a journey. I'm going to take you on a journey from 5 degrees to 2 degrees. So 5 degrees is the temperature increase above pre-industrial levels that we're heading for if we continue with limited climate policies. And 2 degrees is the temperature increase that most countries around the world have agreed would limit dangerous climate change. There will be climate impacts at 2 degrees, but we feel as though collectively we can manage those impacts. So I'm going to take you on a journey through the energy system as we go from 5 degrees to 2 degrees, and I'm going to do it using this very complex figure. But the good news is I'm going to use one figure, and I'm going to try and explain it to you. So first of all, along the bottom we have time. This runs from 1980 up to 2100. And in case you weren't aware, most models of the world suggest the world will end in 2100. On the vertical axis, we have carbon dioxide emissions from fossil fuel combustion and cement production, running here from 0 up to about 100 billion tonnes of carbon dioxide. The interesting part is this grey section down the bottom. These are negative emissions. This is where we take carbon out of the atmosphere, and I'll talk about that in a minute. The easy part of the figure are the historical emissions. Since Cicero started 25 years ago, we've had the United Nations Framework Convention on Climate Change in 1992. We've had the Kyoto Protocol, 1997, the European Emissions Trading System in 2005, and today, most developed countries around the world, including Norway, and an increasing amount of developing countries have climate policies in place. Despite this, emissions continue to grow stubbornly, long-term average of about 2% per year. So climate policy has so far not been successful in changing this long-term trend. But the big question mark for climate policy is, where do these emissions go in the future? And the truth is, we don't know. We don't know what the energy system will be in 2050. We don't know what carbon dioxide emissions will be in 2100. And because of this, we use scenarios. So scenarios are used to explore some of the key uncertainties about the future. Here I show the scenarios used in the IPCC 5th Assessment Report. There are about 1,200 scenarios here, coming from about 30 different models. And from these scenarios, we can learn an awful lot about the way the energy system may develop in the future. These scenarios here, these red ones, are essentially baseline scenarios. That's where we continue with limited climate policies into the future. And perhaps not surprisingly, our historical emissions are following these baseline scenarios. And if we continue along this pathway, in 2100, we'll end 3, 4, 5 degrees, depending on the pathway, above pre-industrial levels. This is what we are trying to avoid. So the goal of climate policy is to move from these red scenarios to these blue scenarios. These blue scenarios give us a likely chance, a 66% chance, to stay below 2 degrees. There are about 120 scenarios here, and if you like, representing 120 different ways that we could get to 2 degrees. And in the next few minutes, I'm going to talk you through some of those scenarios and what they mean at the global level in terms of technologies and assumptions. So first of all, what are cost-effective ways to get to 2 degrees? What's the best way, if you like, to get to 2 degrees? And cost-effective policies are very important for Norway, who likes cost-effective policy instruments. So these scenarios are particularly important for Norway. These scenarios collectively, together, say that it costs around about 0.06% global gross domestic product per year to stay below 2 degrees. It costs nothing. It is free to get to 2 degrees according to these cost-effective scenarios. But to do that, you need to make a few assumptions. and I'm going to talk about three core areas of assumptions. First of all, you need a global carbon price. These scenarios assume that every country in the world, rich and poor, every sector in the world has a carbon price. And that carbon price started in 2010. And if you put that into the model, emissions will peak in around about 2010. And as we saw before, emissions 2015 are growing at 2% per year. After this peak, emissions go down 3, 4, 5% per year for the good part of the century. To do this cost effectively, you need all technologies available. In the world of the scenarios, Jens Stoltenberg's moon landing at Munster was a raging success. Norway is now famous for developing large-scale carbon capture and storage. In reality, carbon capture and storage is much more difficult than we ever thought. We also see a phase out of fossil fuels in these cost-effective scenarios. First with coal, then oil, then gas. By 2100, end of the century, there is a 90% reduction in the consumption of fossil fuels compared to the baseline. And it's not just coal, it is also oil and gas. There is a 75% reduction in the consumption of gas in these scenarios. Gas consumption does increase a little bit at the start, but then it goes down quite rapidly towards the end of the century. And then even after I've assumed we have a global carbon price, I've assumed we have all technologies available, assuming fossil fuels are being phased out, even after we make those assumptions, we need to take carbon out of the atmosphere. We need negative emissions. We've essentially already emitted too much, and to offset that, we have to take carbon out of the atmosphere. And this is a big assumption. So these scenarios require everything to work exactly as planned for the next 100 years. They are very ambitious scenarios. So what happens if we start to relax a few of those assumptions? First of all, we could start to include more realistic climate policies. We could assume that climate policy slowly builds momentum until in 2030 we get a global agreement. And you end up with these scenarios here. So emissions grow to 2030, then we move towards 2 degrees using a cost-effective climate policy. A global carbon price comes in 2030, emissions peak in these models straight away in 2030. Then, in 20 or 30 years, we have an entire decarbonisation of the global economy. Essentially, the fossil fuel industry is gone in 20 or 30 years, and even after that, we still need negative emissions. We can follow these pathways in a model, but I'm not sure whether we could do this in reality. As I've mentioned a few times, negative emissions are very important in these scenarios. There's a lot of negative emissions. Negative emissions are generally obtained in the models when you take carbon neutral bioenergy and combine it with carbon capture and storage. And this is able to take carbon out of the atmosphere. This is a technology that we don't have today. It currently does not exist. It only exists in the models. Here I show the 6 scenarios in this data set that get to 2 degrees without using negative emissions. And you can consider whether you feel that these scenarios are realistic or not. But why are negative emissions so important? Essentially, negative emissions allow us to offset emissions that have happened in the past. So if we emit too much today, we can use negative emissions to offset those emissions. So negative emissions turn out to be very important for the fossil fuel industry. If you want to continue emitting fossil fuels, having emissions from fossil fuels, then eventually you will need negative emissions to offset those emissions. We need to head towards zero emissions towards the end of the century, so anything that goes into the atmosphere has to be taken back out. So essentially, no negative emissions, no fossil fuels. These scenarios here without negative emissions have a very different energy system in the future compared to what we have today. There's no fossil fuels after about 2050, and the energy mix depends almost entirely on bioenergy. It's assumed to be carbon neutral. which is a big assumption at this scale, has a lot of nuclear. We don't like nuclear energy anymore. It has an extreme amount of solar and also a lot of wind. So the global energy system is dependent on 4 energy sources in these scenarios, some of which have big question marks. And you're hopefully asking yourself now, is 2 degrees feasible? This is a question that many people don't like to answer, but I'm happy to give you an answer. Is 2 degrees feasible? Yes, but only in a model. Is 2 degrees feasible in reality? I'd say no, because in reality, climate negotiations haven't delivered emission reductions after 25 years. We're still missing key technologies. We can't figure out carbon capture and storage. We don't even have negative emissions. And we have vested interests. If I'm a fossil fuel company, it's completely understandable that I want to keep emitting fossil fuels. It's my business model. And so even though I'm generally an optimistic person, I think it's going to be very hard to go from these red baselines to these 2 degree scenarios in the real world. And what that means is understanding the consequences of these scenarios in the middle becomes much more important. Thank you.